Good morning everybody. After much discussion on welding and joining technologies for metallic materials, today we will try to focus on that welding and joining of non-metallic materials. So, very few specific non-metals we have considered, for example, the polymeric material and glass and ceramic welding and maybe biocompatible plastic metals that are considered for this module, and we will try to brief discussion on the different welding and joining technologies for this non-metallic material. So, here you can see that we divide the module in the several subcomponent like that. First is try to look into that plastic welding or welding of the polymeric materials, what are the different technology is available, or maybe what are the recent advancement for joining of the polymeric material. We will try to see that first, and then we will discuss the ultrasonic pulse laser welding, which is different from the conventional laser welding process, and that this ultrasonic pulse laser welding so far much application we can see specifically for non-metallic materials, that means specifically for different kind of polymeric materials. Then we will see what are the laser transmission welding process and what how this technique is different from other welding processes, and what is the principle of the laser transmission welding process. Then we will look into the different welding methodologies for glass and ceramic, specifically ceramic materials, and finally we will see that welding or joining technologies, different biocompatible material, plastic materials along with the other metallic materials. So, there are several technologies available, but in principle and this welding techniques for this non-metallic materials is little bit different from the welding processes for metallic materials. So, what is the principle of the plastic welding process? First, we will see the plastic maybe welding process is the process of joining two pieces of the thermoplastic. So, basically we specifically mention that it is a thermoplastic at heated state, and then after sufficient heating with the application of the pressure such that cross linking of the polymer molecules happens, and then join between the two components of the plastic material. So, in principle it is same the conventional welding process, because here we need a source of heat. So, that source of heat may be different, and difference as compared to the conventional welding process is that how we can utilize the source of heat and how we can control this source of heat, which may be applicable for the joining of the plastic materials. So, plastic can also be joined with or without the filler materials depending upon the applicability and the different components, but normally we can divide into two categories like that. The welding or joining forms in case of the glass parts for the amorphous polymers that we consider as a reference for the glass transition temperature. So, that cooling should be done below the glass transition temperature for the amorphous polymers, and then after cooling period then the joining of the two plastic components actually done. Or in case of crystalline polymers, we consider that as a reference for the melting temperature. So, as by heating it goes above the melting point temperature, and then during the cooling phase it comes back below to the melting point temperature, and then after the cooling period the joint between the two plastic components can be done. So, if you look into more details that welding techniques for polymeric melting, in principle that from the figure if you see the right hand side, when the two interfaces come in contact, there is no heating, if there is no application of the heating, and then partial heating and that time t greater than 0, and finally we reach the complete heating after sufficient time. So, in principle that interfaces basically conform with respect to each other such that intermolecular diffusion and chain entanglement actually occurs, and that actually is responsible for forming of the welding or joining between the two polymeric materials. So, healing of the interfaces is basically due to the diffusion of the polymers chains, across the interface. So, here one important point is that the diffusion of the at the interface of the polymeric chains happens, and advantage in the point that in case of metallic material we can find out that there may be the possibility of oxide layers. Most of the cases we can, and it say if you want to get a good diffusion bonding between the two surfaces in contact, then it definitely needs to remove the oxides layer, but that is not, that problem is does not exist in case of the most of the polymeric materials. So, in that case polymeric materials, it is without any surface preparation also. When the two plastic components come into the contact, and if we apply the proper heat and pressure condition, then it is possible to join the polymeric material. So, in that sense it is advantageous as compared to the metallic material, but degree of welding in case of polymeric material we can find out that it depends on the material properties, temperature and interfacial pressure and time, also all are the complex function, and then with the proper choice of all these parameters we can expect good bonding or good joining of the polymeric materials. As I mentioned that amorphous polymers basically the must be heated above the glass transition temperature, or semi-crystalline polymers or crystalline polymers the above the melting point temperature. But here one point need to mention that thermosets cannot be welded without the addition of a tie layers. So, in principle the welding of thermosets is different from the thermoplastics. So, thermosets polymers can be welded with the help of the tie layer, that is normally thermoplastic layer. If you put it, and then it is possible to join the thermosets polymers. This is actually the characteristic behavior of the thermosets are different from the thermoplastics. So, that is in case of joining of these thermosets we need to consider this in principle that there is a application of the or the intermediate layer of the thermoplastic is required to join the thermosets plastics. So, now we will try to look into the different types of the plastic welding. So, different processes for the welding of thermoplastics that are hot gas welding. So, these techniques actually already developed, and that hot plate welding, ultrasonic welding, spin welding. So, here you can see that hot gas welding. So, simply you can use the stream of the hot gas, and that if you control in such a way that it is responsible to fuse the to melt the contact of the interface, and then we can join the two plastic material component. Then similar to hot plate welding, instead of directly using the hot gas stream, here we can use the metallic plate, and that metallic plate is basically control the amount of the heat, and then it is responsible to joining of the two components. Then ultrasonic welding. So, ultrasound vibration if we create, and that actually that ultrasound vibration is basically creates in a very small localized area the frictional energy, and that localized area in a small part the frictional energy is basically melt heat the sample, and that is then after that welding can also be done. Similarly, kind of spin welding. Spin welding is the similar kind of the friction welding, and then vibration welding. There is another division of the plastic welding is that vibration welding, friction stir welding, and radio frequency welding. So, if we see the vibration welding means we can use simply mechanical vibration, and that is in similar principle of ultrasonic welding. We can join the two plastic components, but there is a minute difference between the ultrasonic welding and vibration welding as well. Friction stir welding and radio frequency welding, these are the two recent developments of the joining of the plastic components. So, friction stir welding we have enough discussion on this for the joining of the metallic materials, it is a established process, but friction stir welding still it is under development in specifically for joining of the plastic components. We will try to discuss that up to what level the joint strength can be achieved using the friction stir welding process. Then radio frequency welding is specific frequency welding we generally observe in case of plastic welding. So, all these welding process we will try to discuss in details in the successive slides. We can find out that hot gas welding, so simply hot gas welding is a plastic welding process simply utilizing the heat of the hot gas stream. So, actually with the application of the hot gas stream, we apply until and unless it soften the material, and then after softening the material with the application of the pressure, then that material becomes harder and during the cooling phase. So, from the figure it is obvious that at the interface using the hot gas stream we can heat the samples, and then after that we need to apply the pressure. So, the job of this hot gas stream is that simply soften the filler material if there is any use of the filler material, as well as the soften the base material. Then filler material is pulled, or actually when we use the filler material is actually pulled or fed into the joint. And then finally, the polymeric molecules are cross linked, and when the workpieces basically cool down, and finally cool down, and as a result it forms a strong joint between the two plastic components. We can see the hot gas welding, the several application of the hot gas welding, and that producing the plastic containers and producing the tanks for the storage chemicals, and here ventilation ducting, tubes. We can find repair works, different types of repair works. We can very easily use that hot gas stream for joining of the plastic components. But one important point is that if the polymeric material having the tendency to oxidize at very high temperature, then instead of hot air we can use the stream of the hot nitrogen, because at the same time nitrogen actually protect this oxidation of the plastic polymeric materials. So, if we see that schematically that hot gas welding looks like this, that there is a welding rod, and the welding rod is basically fed directly at the interface between the two plates, and at the same time there is application of the pressure, and if we see continuously there is a forming of the weld bead. So, here you can see with this is the welding rod, and there is a continuous feeding of the welding rod. At the same time here we can apply the pressure, and then there is a continuous form of the welding bead. But this to sharpen this welding rod, there is a air heater we can use, and through the nozzle, round nozzle, the hot air passes through at the interface, and at the interface there is a this creation of the front wave simply by application of the hot gas stream is actually try to soften the material, and then finally there is a continuous movement of along this direction, that is the welding direction, and it creates the weld joint between the two components. So, this is the techniques for the hot gas welding of plastic components. Now, next we will try to discuss the hot plate welding. So, in the hot plate welding also instead of the continuous hot air, we can use as a hot plate to heat the plastic components, and these hot plates are placed between the surfaces to be joined. So, workpieces are placed to the plate, and then gradually heat off, and then finally it soften that plastic component. So, after a predetermined time of the heating, then the plate is removed. After then parts are come in contact between two components, and then press and finally fuse together. So, polymeric molecules with the same principle cross link with respect to when the workpiece cool down, and then finally it forms the weld joint. So, here the only difference in the hot gas welding is simply instead of using the directly in a very small focused area the hot gas stream, here we can use the hot plate. So, hot plates, but hot plates is mainly used of the aluminum alloy, and we know that aluminum alloy is having very good thermal conductivity and equipped with an electric heating. So, electrical conductivity is also good for the aluminum alloy, and then a thermocouple is in the hot plate welding machines. The thermocouple is also provided with this system, so that we can control the temperature, and this is the working principle of the hot plate welding. Now, where we can find out the typical application of the hot plate welding, that components of the domestic electric devices such as dishwasher, washing machines, vacuum cleaners, several components, it is possible to join using the hot plate welding process. And then different pipes can also be that joining of the pipes can also be done using the hot plate welding process. Other automatic components, for example, lights, fuel tanks, reservoirs, batteries, here also we can find out the application of the hot plate welding. What if we see the advantages of the hot plate welding, main advantage is that it is a easily automated, and by deciding the size of the hot plate, looking into the component size. Then high quality tight joints can also be done, and very large parts may be welded. That is the one advantage as compared to the hot gas welding, because hot plate welding depending upon the size of the plate. So, a large area can be covered in case of this hot plate welding. But hot plate provides conforming the joining surface, that means joining the two surfaces, but the disadvantage of the hot plate welding, that long welding cycle time, that means the total welding time is relatively very high as compared to the hot gas welding processes. So, normally welding cycle typically 20 seconds for small parts and up to 30 minutes for the large part. So, there is a that is the disadvantage, is in the sense that there is a huge time, welding time is required in case of hot plate welding. So, that means rate of production may not be very good in case of this welding techniques. And other disadvantage is that relatively large amount of the flash, that means excessive materials can be forms in this welding process. So, we surface aesthetic point of view, this hot plate welding is not good as compared to the other plastic welding processes. Next, we will try to discuss on the ultrasonic welding process. So, with the principle of the ultrasonic welding process we have already discussed, but here we can see that two workpieces are actually bonded as a result of the pressure. So, there is application of the pressure, but parts with the along with the application of the high frequency acoustic fiber. So, that is the principle of the ultrasonic. So, high frequency acoustic fiber acoustic vibration causes actually oscillation of the material, and it is a friction between the parts, which is basically creates the situation of the local heating of the contact area. So, normally this high frequency acoustic vibration creates the frictional heating, it is very small confined area. So, therefore, the plastic melts in the contact area, and then the polymer molecules are cross linked and finally form a strong joint. So, in the figure we can see the workpiece material, we can put here also, and this is the vibrating element and creating the vibration, and the local area we can create the that local area we can generate the frictional heat, and then can be joined this thing. Let us see what are the process parameters in case of ultrasonic welding process. So, if we see the typical process parameter, ultrasonic welding cycle takes about 1 second, that means very small time as compared to the other welding processes. The frequency of acoustic vibration range from 20 kilohertz to 70 kilohertz. So, very high frequency vibration, acoustic vibration is created in this process, and the amplitude of the acoustic vibration is very small, only 0.05 millimeter, or we can say the 50 micrometer only. So, in that range the amplitude of the acoustic vibration. So, that is why the thickness, that means affected zone by the very localized frictional energy, heat energy is very small, it is a very localized. So, therefore, thickness of the plate welded using by this power is normally small, but it is decided by the power of the ultrasonic generator. So, therefore, ultrasonic welding process is mainly used for the processing of the amorphous materials, polymers, for example, the polystyrene PS and ABS. So, this kind of polymeric material normally used by using the ultrasonic welding processes. So, apart from this material, we can see there are several other application area using the ultrasonic welding process, such as medical equipment like filters, phase, mask, valves, gradiometry reservoir. So, all this typical medical equipment we can find out the ultrasonic welding process. Then automatic components, glove box, doors, filters, valves. So, these are the automatic automotive components can also be welded using the ultrasonic welding process. And we can see that any other appliance devices, that means vacuum cleaner, steam iron, dishwasher components can also be done using the ultrasonic welding process. So, electrical equipment, switch, terminal, blocks, connectors, all can be done that using the ultrasonic welding processes. So, even for toys also we can find out the application of the ultrasonic welding process. So, definitely the advantage, having certain advantage with the several application area of ultrasonic welding process, mainly is the short welding cycle time is short, cycle time is very short, and of course, these machines can also be easily automated and can also be controlled. So, therefore, when there is a good controlling of this instrument, then it is easily can be focused in a very small component, also joining of very small components of very small thickness. So, another advantage is the small amount of the flash can form. So, there may after welding there is a less amount of the material flash is required to remove. So, the small amount of flash formation is another added advantage, and low energy consumption as compared to the other hot gas, or maybe we can say the hot plate welding processes. But only disadvantage in that in the sense that small components parts can be welded. So, it is a very big components cannot cover in the when there is a requirement of the very big components to be welded, and definitely proper tool design is also required. So, that in these cases the tool design is more a significant component as compared to the other welding processes. So, that is the advantage. So, therefore, in overall we can say that ultrasonic welding is a very promising technology for joining of the plastic components, and it is a very thin components can be joined more easily, and rate of production is also very high as compared to the other hot gas or hot plate welding. So far we have studied. Now, another welding processes, that is spin welding process. Spin welding process is a plastic process. It is a similar principle to friction welding processes, in which two cylindrical object parts can be brought into contact and they can be joined by the friction pressure, and definitely one of them should rotate with respect to having that means some relative rotational velocity between the components, and then friction between the parts is as a result in for the generating of the heat, and after predetermined time the rotation stops, and then molten regions of the work place actually fuse together by application of an axial pressure until the joints is cooled down. So, we can keep on holding the axial pressure till the joints cool down to the room temperature. So, typical application is used for the manufacturing of the aerosol bottles, floats, and the other circular components we can by using the spin welding process. We can see that how it works, spin welding process. So, drive two components, one drive starts rotating component, the frictional rotating, and component blocked again rotation, that means keep it stationary. So, then after rotating start rotating, and then we keep in contact the interface between the two components, and then finally material is plasticized and weld bead is formed with the application of the axial pressure, and the fourth stage rotation is blocked. That means we can keep on we can block the rotational speed and then keep on holding the axial force until and unless it is cooled down to the room temperature. So, we can find out the flash form on the at the joint interface. So, it is a kind of similar kind of technology that we can find out in case of conventional welding process, that is the friction welding processes. So, this is one this is the principle of the spin welding process, but the main advantage of this process is the reproducibility, that means reproducibility with the similar welding conditions, and large parts can also be welded, and high quality weld can be achieved, and oxidizing polymers may also be welded, because oxidizing polymers, if it is forms the oxidized layer, it can be removed in the form of a flash from the outside of this joint interface. So, that is why it is advantageous in that sense, but main disadvantage, then we can say the limitation of this process is that at least one parts to be is the cylindrical symmetry, circular symmetry. So, that should be welded joint, and minimum rigidity required. So, that means when the circular part is supposed to join, that the rigidities of this components is the one constraint for this kind of spin welding process, we can say the friction welding process. So, we will try to discuss in details on the friction welding process later on also. Next, we will try to look into that another welding process, that is called vibration welding. We can give a separate name, the vibration welding process, as compared to the ultrasonic welding process, because in this vibration welding process we can use the simple mechanical vibration. So, vibration welding is a process in the plastics welding process in which two workpieces are vibrated with a certain frequency and amplitude, and then in this case the parts actually rubs against each other under the application of a pressure, and that with that situation it causes the friction between the surfaces, and that friction is responsible to generate the heat at the interface. So, therefore, heat results in the melting polymer in the joint region, and the two workpieces actually fuse together after a predetermined time, and when we fuse together joining with the stop the vibration, and then polymeric materials are cross linked, and the workpieces cross linked after the cooling down of the workpieces, and finally it forms a strong joint between the two components. So, therefore, we can see that in vibration welding process, that it is a different from the ultrasonic welding process in terms of the amplitude of the vibration and frequency level also. We can see that typical process parameters in the vibration welding process, that here the vibration welding cycle is very short, even in vibration welding cycle is very short, that means even in millisecond also, that frequency of vibration is in the range of 100 to 500 Hertz, but in case of ultrasonic welding process, the frequency of the vibration was in the on the order of the kilohertz. So, in that sense the frequency level are different in these two cases, and amplitude of the vibration, here is a wide variation is possible 0.5 to 5 millimeter, but in case of ultrasonic welding process the amplitude of the vibration was very small, even it was confined to only 0.05 millimeter, only 50 micrometer, but here we can range the amplitude of the vibration from 500 micrometer to 5000 micrometer. So, in that sense it is different from the ultrasonic welding process. So, here also we can see the most polymers, for example, amorphous, semi crystalline and crystalline produced various fabrication methods, basically the thermoforming, extrusion, injection molding, blow molding, compression molding, transfer molding, that type of material can be welded using the vibration welding process. Here you can see the application of the vibration welding process is used in the automotive and domestic applications. So, advantage we can see the oxidized polymer can be welded, that was also in case of friction welding, or we can say spin welding also, we can find out that oxidizing polymers can also be welded. Easily automated in this case, very high productivity because cycle time is less, and the large and complex parts can also be welded using this kind of welding process. But disadvantage of this thing, the unit to produce the vibration, the relatively expensive equipment, and of course, some minimum rigidity is also another requirement, or I can say that it is another limitation of all this process. So, there is a new development also, that conventional friction welding process we can find out in a metallic material, that can also be applicable in case of joining applicable, or people have tried to apply the friction stir welding process in case of plastic or polymeric material. Here you can see the typical characteristic of the friction stir welding process, but before that, friction welding we have already discussed that definitely friction welding, the relative motion between the two parts are required and results in the frictional heating. But apart from frictional heating, if there is a stirring action can also be added, then we can say it is a friction stir welding process. So, in case of linear and orbital welding process, a wide range of geometries can also be welded. But in case of spin and angular welding process, we can find out the circular weld geometries is the best suitable geometry configuration that can be welded in case by the principle of the friction welding process. But friction stir welding process for polymeric material, we can see that with the application of polypropylene sheets, here we can see that two plastic sheets are in contact, and in between we can use some tool, and at the tool rotational that generates heats, and that at the same time there is a linear movement of the rotating tool, that means along the welding direction. So, this is the principle of the friction stir welding process. But using this process, it was tried to that polypropylene sheets for joining of the two materials. So, 15 millimeter thick plate have tried the using by simply by converting the traditional milling process with 8 millimeter diameter and 6 grooves and 30-degree groove slope basically. So, here we can use the tool. Tool is having we can say it is a kind of threaded tool. So, that threaded tool is used for the application of the polymeric materials and under the head of friction stir welding process. So, here the translation speed was 400 millimeter per minute and the rotational speed was 630. So, using this friction stir welding process, but although it is a promising technology for the joining of the even for non-metallic materials, plastic materials, but it was not very much successful because only 50% of the base material strength was achieved by these welding techniques. But what was the, if we look into the typical characteristic or typical characterization of the weld joint, we can see the crystallinity is basically reduced in the seam. Definitely there is a stirring of the material in the seam, that means amorphous content is more higher in the seam than with respect to the matrix material. So, that means at the exactly at the seam joint the crystallinity is reduced. So, that may be the one reason that we are getting the very small amount of the joint strength as compared to the base material. Then cohesive strength at the interface between the matrix and the seam, this is another characteristic behavior we can find out, that at the interface between the matrix and the seam we can find out the cohesive strength, but matrix fracture surface as significant then we can find out the fracture surface matrix fracture surface we can find out the significant embrittlement, and then these are the typical characteristic behavior we can find out for the friction stir welding of polymeric material. But definitely to achieve a good weld joint strength, there is a need of optimization of the parameters and of course, optimization of the tool geometry is required. But further investigation on this process is required specifically for polymeric material. There is another new welding techniques we can observe in case of joining of the plastic material, that is radio frequency welding. So, sometimes also it is called as dielectric welding. So, here internal heat is actually generated by the dielectric hysteresis losses in the thermoplastics. So, there is a rapidly changing of the electrical field that actually results in the intermolecular friction and heat generation. Therefore, we can find out the intermolecular friction and heat generation that is due to the rapidly changing of the electrical field. So, in that principle the radio frequency welding techniques has been developed in case of the plastic materials. So, here you can find out the typical cycle time is 1 to 5 second. Therefore, we can say the relatively fast process as compared to the other existing process, and then used for the very thin sheet 0.03 millimeter, but at the maximum 1.27 millimeter sheet can also be done using these techniques. And the material must have high dielectric losses, then only this process can also be applicable. For example, most of the PVC that material, most common material, this generally joined by the radio frequency welding process. So, application we can find out the packaging area, welds and relatively appealing cosmetically. That means, the cosmetic aesthetic appearance of the weld joint is very good in this case. So, therefore, we can find out the tremendous, mainly the packaging industry, we can find out the application of this kind of joining process. So, this aesthetic aspect is very good in the radio frequency welding process, and other reason is that it can be well controlled process, and this process remotely used and can also be remotely used. Therefore, in that sense the packaging industry can find out the very good application for the radio frequency welding for polymeric materials. So, but advancement point of view we can find out that there is a advancements also happens using the additives and consumable of the non-polar materials can be used, can be sealed using the, that means in case of the using the additives and the consumable non-polar material, using this radio frequency welding can also be done. So, other improved, that means machine design with the automatic tuning of the power supply, quick changeover of the tooling, that means there is a advancement in the development of the radio frequency welding machines for in case of joining of the plastic materials also developed nowadays. So, after this different welding of the plastic material process, we can see that there is another welding techniques, that is called ultra short pulse laser welding techniques. So, this welding technique is completely different from the conventional laser welding process. There are also pulse, the only difference is the ultra short pulse laser welding, that in terms of the pulse duration, and in principle there is some mechanism of the heat generation are different as compared to the nanosecond, or we can say that microsecond or millisecond pulse laser. So, here you can see the ultra short pulse laser, or sometimes it is called ultra fast laser, is a laser that actually creates the pulse over the duration of the femtosecond to the picosecond level. So, therefore, since that pulse duration is very small, normally we can create the very high power and low amount of the pulse energy. So, in principle the ultra short pulse laser is simply apply the pulse energy within the very short duration of the time. So, that time, that short duration, that duration of the pulse in ultra short pulse laser process is basically is the comparable as compared to the relaxation times within the metallic material, or in any case of other non-metallic material also. So, extremely high power in ultra short pulse can be achieved using the holonium doped YAG laser crystals. So, therefore, HO-YAG laser is usually operated in case of pulse mode also, but even there is a development now also development of the ultra short pulse fiber laser also, so that it creates that very small duration of the pulse. So, definitely the ultra short pulse laser emits laser pulse extremely short pulse, typically in the range of 10 femtosecond or 100 femtosecond, 10 maybe at minimum as 10 femtosecond. So, 1 femtosecond is equivalent to 10 to the power minus 15 second, and the range between the picosecond also, the picosecond means 10 to the power minus 12 second. So, therefore, since duration is very high, the very high peak power, then peak power density is often is also very high as compared to the conventional laser, but the main process parameters for ultra short pulse laser are the less than femtosecond laser pulses, or maybe or the order of the femtosecond pulse laser. So, energy pulse from the nanojoule to microjoule, that range of the pulse energy, and pulse repetition rate can vary as much as kilohertz to the 100 megahertz within that range. So, there is a wide applicability of this ultra short pulse laser nowadays is observed in case of metallic or non-metallic material. So, average power here you can find out that it varies from 1 watt to 100 watt. So, average power is quite low as compared to the other high power or maybe conventional laser processes, but the main significant point in ultra short pulse laser is that very high peak power, and application of the pulse energy over a femtosecond duration of the time. So, definitely there is some characteristic difference with the application of the ultra short pulse laser, which cannot be explained by the or maybe which cannot be applicable for the conventional laser welding processes. So, since Laser energy. Now we will try to discuss this ultrashort pulse laser welding process in the with the perspective of the application in non-metallic material. So, laser energy of femtosecond pulses actually absorbed by the nonlinear process is utilized as a heat source for frictional welding of the glass. So, normally we can find out the huge application of the ultrashort pulse laser for the joining of the glass. So, extremely short pulse duration basically allows the nonlinear absorption of the energy by the material, which differs from the conventional absorption process leading to the non-equilibrium states in the process region. If you see the figure, the representative figure here, you can see the application of the ultrashort pulse laser with the application of the conventional laser at the interface. There is no absorption and the all energy is transmitted through this material, and if there is a at the interface there is a minimum amount of the absorption or there is no absorption, and if we use the glass material, and of course, but if you use the ultrashort pulse laser. So, ultrashort pulse laser says that there is a non-linear absorption at the interface because of the non-equilibrium thermal non-equilibrium state actually exists with the application of the ultrashort pulse laser. So, that means application of the pulse laser is so fast that the heat energy is absorbed at the interface, that but similar material cannot absorb the laser energy if we use the nanosecond or microsecond or millisecond laser pulse laser. So, therefore, while the linear absorption requires an opaque material, but nonlinear absorptions even in the transparent material at high energy densities can also occur at the interface. If we see the processing principle of the ultrashort pulse laser is that nonlinear absorption process is observed, the laser pulse energy is deposited only within the focal region, which actually leads to the very localized melting of the sample. So, another advantage is that with the application of the ultrashort pulse laser, so that heat affected zone on the surface is very small, which is not comparable as compared to the conventional laser welding processes. So, laser focus is placed at the interface, and then the combined action of the nonlinear absorption process and heat accumulation occurs within that period, that actually leads to the welding of the sample. That is why this process is mostly can be mostly applicable, we can find out in case of glass. So, if the time between the successive pulse is shorter than the time required for the heat diffusion, that actually happens in the in case of ultrashort pulse laser application. So, therefore, there is a stepwise increase of the temperature. So, temperature may not, with the application of the pulse laser, there may not be continuous increment of the temperature. So, temperature actually increases and the stepwise. So, the glass, that means optical transparent material, can be locally melted and resolidification with the application of the ultrashort pulse laser. But at the same time, the cooling rate is also very fast in this case. So, therefore, the solidified glass exhibits at the higher effective temperature. So, that defines the actually defines by the indication of the structure of the glass. So, that is comparable as compared to the non-laser modified glass, because that in the ultrashort pulse laser also there is a high rate of cooling we can observe. Joint formation is similar to conventional processes. Simply by moving the laser, continuous welding seam can be induced, but if the laser focus is at the interface of the sample, resolidification occurs of the molten material, and that actually creates the strong bond. But in cases that baking state, definitely the mechanical properties can also be improved, or mode of material joining can be decided by the repetition rate of the applied ultrashort pulse laser. For if we see that in general, the very low repetition rate in case of ultrashort pulse laser and low repetition rate at the same time, the high pulse energy is more suitable for the material ablation process. So, simply vaporize the metal very quickly, but in other way that high repetition rate, but low pulse energy is mainly suitable for the joining of the welding mode of the material. So, therefore, but this is more suited for the joining of the glass using the ultrashort pulse laser, mainly having the two advantage, because there is a one advantage is that even for the transparent glass, is joined by the nonlinear absorption by the application of the ultrashort pulse laser, and that heat affected zone is localized or melting can be localized in a very small zone. So, that means overall heat affected zone is very small as compared to the other welding process, or we can say it is a very controlled heat affected zone can be produced by the application of the ultrashort pulse laser. So, apart from that, the no annealing step is required to strengthen the bonds materials with the widely different thermal expansion and coefficients can be easily joined in case of that. Means the using the ultrashort pulse laser also there is an advantage yes by joining of the dissimilar combination of the materials which cannot be produced as by using the simply conventional welding process. That means it is a medium or short range of the pulse of lasers. No thermal or shock wave damage can be observed as compared to the long pulse laser duration and the high peak power. Actually, the thermal or shock wave damage mostly decided by the pulse frequency here. Limited heat affected zone, definitely we have already told that limited heat affected zone can be produced using this long pulse laser. Therefore, since limited heat affected zone is produced, therefore, thermal induced stress also very less in this or maybe minimized in this type of material. The workpiece follows the very high rate of heating and cooling over a narrow zone as compared to the long pulse laser. That is also another advantage of this joining of the ultrashort pulse laser. So, we can find out the typical application and limitation of the ultrashort pulse laser welding process. So, materials using different types of the glass, so far we observed by the application of the ultrashort pulse laser. Fused silica, borosilicate glass and ultra low expansion glass, that are the typical materials mainly used for the ultrashort welding process. But limitation is that development of suitable delivery system, that means jigs, design of the jigs and fixture and the focusing, that means focusing of the laser and a very defined zone is the that is the main limitation of this process, and definitely cost is another important criteria for the wide application of the this welding process. So, we can areas of application we can find out using the ultrashort pulse laser, that is the biomedical. So, we can pass through the optical biomedical, we can find out the so many medical devices can be welded using the ultrashort pulse laser. Even for 3D imaging process also we can find out the ultrashort pulse, we can find out this application of the ultrashort pulse laser. Ultrashort pulse laser typical, it is very much suitable for the micro fabrication and rapid prototype is another application area of the joining of the ultrashort pulse laser.